Okay, hello, welcome. Greetings, everyone. Happy to see you all here. Today we're going to be talking about MESA and GYRE. So I want to thank the organizers for inviting me to give this tutorial. I think it's a really wonderful idea to teach people how to use this code because it's so pervasive in our community. I also want to echo the sentiment given by Connie yesterday about being inclusive to everybody. So this is really a tutorial meant to bring people from any level up to being able to use MESA, at least in a basic capability. So I'd like to explicitly welcome any kind of question, any kind of difficulty that you encounter. And to that end, we have three TAs who are helping. So we have Lynn Bouclet, we have Meredith Joyce, and we have Matthias Mikkelsen. So they'll be helping you out with your questions. You can raise your hand and ask a question, and if it's quick, we can try to address it on the spot. Otherwise, someone can come and try to help you. And otherwise, you can also post your question on the Slack. And there's some people monitoring the Slack trying to answer questions. And if we can't answer the question, we can also post it on the MESA users list. And then we go to really the global MESA community. So there's really a lot of MESA expertise in the room, and there's also a lot of general stellar pulsation and evolution knowledge in the room. So there's numerous MESA developers here. There's myself, there's Meredith, there's Warwick Ball's at the conference, and I think, yeah, Rich Townsend's here. So Rich made GYRE itself, so he's really the wizard. And then there's, authors of other stellar evolution and pulsation codes like Jörn in the audience. So really, we should be able to answer your questions. And then, for the more theoretical knowledge, we have, authors of textbooks on these subjects in the room as well, like Connie and Jörn and so on. So yeah, so let's get started. So I've posted in the Slack some introductory instructions. Before we get going, can I see a show of hands? Who has used MESA before? Okay, nice. Most of the room, but we won't assume any of that. Who's used GYRE before? Okay, similar people. Who's used a different stellar evolution or pulsation code? Okay, yeah, very good. Okay, very interesting. Who has MESA installed currently? Okay, almost everybody. Okay. Yeah, that's also a good question. Yeah, most of the things I'll be showing probably don't require the latest version, but if you don't have the latest version and something doesn't work, that's most likely the reason why. Okay, so let's begin. So we'll just go through a quick installation first, and let me take out a timer. Well, I guess the clock is my timer. There's an hour and a half, right? It's 10:30 it ends. That works. Yeah, okay. Yeah, that works. Yeah. Okay, fantastic. Okay, so there's instructions on the website that you can and should certainly go through, but also I've prepared a little installation script. So this, by the way, is available on this GitHub repository, which is also hosting the tutorial itself. If you're not able to go through the materials today, all the materials that I'll go through are available online, so you can revisit them later. But also, we'll just have you clone or download this repository. So for those of you who know how to use Git, it's a simple matter of you can go here, okay, github.com/Earl Bellinger. That's me, by the way. I don't think I said my name, so nice to see you all. And then MESA-GYRE-tutorial-2022. And then you can copy this, and then you can git clone it in your terminal. And that should work. Alternatively, you can download a zip, probably even easier. If some of you have cloned this already, and I saw from the graphs that several people have, you'll want to pull. You'll want to git pull the latest version because I've made alterations even just yesterday. Okay, so now we have it. You can see the directory structure is the same as that on GitHub. So we can take a look. I can make it increase size. So in the source directory, I included this script called install MESA. And yeah, as you'll see from this comment, it's intended to be run line by line. There's no error checking involved or anything like that. So it's just for convenience. So the first thing we'll do is we grab the latest version. I'll grab this whole block and just paste it into my terminal. So what are we doing here? We're saying we want MESA version 22.05.1 and the SDK version 22.6.1. If you're not using Linux, you probably want a different version of the SDK. And you can get that on, yeah, you just go to the installation instructions that I put here, and you can follow the links, and you can find the version that's appropriate for you. Also, if you run into problems throughout this installation, probably there's an FAQ on the website that answers your specific problem. And if not, we'll handle that. Okay, so now we'll make a directory called MESA and go in there. And we'll download the SDK. So that all this is saying is we're going to grab this version of the SDK, and then we're going to use curl to download it from the command line. Now, there's a lot of people in this room sharing an internet connection. If you haven't already done this, it might be prohibitively slow. I can see 7 minutes left. So again, if we don't have time to download everything live, you can just follow the show, and we do it later, you know, over time. So I can see that's already going to take quite some time, so I might as well talk about some other stuff in the meantime. So for those of you who don't know, MESA is a stellar evolution code. So the basic idea is that you want to calculate theoretical evolution of stars. And it can handle a wide variety of different types of stars, actually going down to some types of planets, and then going up to very massive stars. It can handle all kinds of evolutionary stages and all sorts of different interesting physics, which I don't have time to even touch how many things are there. So the MESA website is pretty nice and comprehensive. A lot of you will have gone through this installing MESA section. And then using MESA, there's a lot of information here. On running MESA and getting the outputs and building enlists and so on. We're going to be doing some of that today, but not using these official materials. And then there's documentation for all the different modules in MESA. So MESA is modules for experiments in stellar astrophysics. And each of these modules can be used on their own. So like if you need an equation of state for some independent project, you can use the MESA module for that. Most of the time, you'll spend a lot of your time in these reference materials for the star defaults because that's the main way, that's the main driver into calculating a stellar evolution model. So in the MESA references, you can go through the controls and the star job controls. This tells you things like, you know, the mass of your star or the initial metallicity of your star and so on, when to stop your run, etc. There's an extensive test suite in MESA. This has a large number of examples of different types of stars that MESA knows how to make. And so you can use these as a starting point for different types of projects you want to work on. For example, if you want a 5 solar mass Cepheid going through a blue loop. If you want to calculate a 1 solar mass track going from the pre-main sequence all the way to a white dwarf, etc. You can look through. There's an extensive list of things that you can work on. Okay, the time has gone up to 18 minutes, so we certainly won't have time to follow the installation live. But I'll just tell you quickly what the rest of the script will do so that when you run it line by line, you won't be confused by what's going on. So right now we're on this step where we're downloading the MESA SDK. So the MESA SDK is a set of compilers that allow you to run and install MESA. So it has things like G4tran and so on. And this is also made by Rich, so all the detailed questions can go to Rich. Incredibly useful, by the way, not only for using MESA, but for other things as well. So this script will make a directory for the SDK. It will untar this file that we've downloaded into there. I like to make a symbolic link, not super important, but it points to the MESA SDK. And then in my bash RC later, I add this line, export MESA SDK root to the bash RC. And that means that every time we open up our terminal, well, that'll come later, but every time we open up a terminal, we'll have as an environment variable where the MESA SDK is loaded. And then this line will run the SDK. Now we'll go on and download MESA. So we say we want this particular version. We'll download it from Zenodo. It has a permanent hyperlink. We'll unzip it. We'll again make a symbolic link. And we'll add this environment variable of MESADIR. Tells us where MESA is located. We simply go into that directory and we hit install. And these are also the first steps. Sorry, I should go to the top here. These are the first steps in the tutorial that I've linked on the website. So yeah, so if you've downloaded this directory, hopefully many of you have downloaded or cloned this directory now. I'm going to cancel that installation. So you now have this directory structure where we have the same stuff as on the Git repository. And the first thing you might see here is this tutorial.ipynb. So this is a Jupyter notebook. So in order to load this up, you're going to want to start a Jupyter server, which is as simple as calling Jupyter notebook in your terminal if you have Anaconda Python installed, which is something I mentioned in the Slack channel. If you don't have Anaconda, you can go to anaconda.com and get it. You can also, of course, get Jupyter without Anaconda, but it includes also all the packages that I'll have used today. Yeah, so if you have that set up, you should be able to call Jupyter Notebook, and then you get out this. It'll open up your browser, and it'll show you where these files are located. And so you can navigate to the MESA GYRE tutorial, and you can locate tutorial.ipynb. And when you open it up, you should see this nice page telling us that we're at TASC6 on this tutorial on stellar models for asteroseismology. And yes, so the first step is about the installation. And so that's what we've been going through. And when we've gotten to the point that we just got to in this installation script, you should see MESA installation was successful. Since most of you have installed MESA already, you've already seen this nice message. For those of you who haven't, hopefully you get there. Yeah, since the connection is slow, just let us know later if it worked out, and if not, we can try to help out. So the last steps of the tutorial are to install GYRE. Here, this might be a step that many of you haven't done already. So GYRE comes with MESA, so it's a simple matter of pointing your GYRE dir to the place in MESA where it comes bundled, and you probably have to call make inside that directory. And then the last bit here is to add these lines to your MESA, to your bash RC, so that every single time you open up your terminal, everything MESA related will get loaded up, and you'll be ready to go. So it will add the location of the SDK, the environment variable. It'll add the MESA directory, the GYRE directory. We'll set the number of threads, OMP num threads. So MESA uses OpenMP for parallelism. If you have a slow machine, or if you are not using a power source, you might want to set this to 1. Otherwise, you can use a larger number of threads. Maybe like 12, for instance, if your machine supports it, is a good number. And then finally, we initialize the MESA SDK every time we load up our terminal. Okay, wonderful. So now, in theory, we are ready to go with MESA. So let's do our first MESA run. But before, let me pause for a moment and ask if there's any questions or difficulties along the way. What's that? So far, so good. Fantastic. Okay, so let's do a very quick first MESA run. So MESA inside the, let's take a look in our MESA directory. So if we ls MESADIR, I should make this larger so that you can see. Is there? It might be Control Plus, right? Can I just do Control Plus? No.
And also the top of the menu has magnifiers.
Control Shift Plus.
Thank you. Oh, there we go. Very good. All right, this is now visible. Okay, so if we ls MESA-dir, you can see all the modules that come packaged with MESA. The main one you'll be interested in is star, because we're looking at making stars here. But of course, there's lots of other helpful things. You've seen there's GYRE in here already. There's like a binary module for doing binary star evolution, all the documentations and docs, stuff like opacities, etc. You can look around. There's lots of useful things. The main thing we're interested in is star. So if we ls MESA-dir star, yeah, there's this nice work directory that's set up for you, which is a good starting point for a fresh project. The other alternative is starting from a test suite case, which you can also see in here. There's test suite, and there you see all the test suite cases. But what we're going to do is we're going to copy over this this work directory. Now I already have a work directory, so I'm gonna move the work directory that I've included in this Git repo to a different location so that I can run the tutorial fresh. If you're not running MESA yourself on your laptop right now, you can just keep this work directory right there, and the Python notebook should work. That might also be convenient. So I'll move work to work complete. And now what I'd like to do is copy over a fresh work directory. So I'll copy this. And now we have a new work directory. And I'm also going to copy over the defaults, which isn't normally there, but we'll take a look at that. So now when we go into work, we have a number of things here. We have a few scripts: clean, make, re, and run. And then we have a few files: enlist, enlist project, enlist pgstar, and then these .list files. So the scripts, clean will help you like start fresh in your directory. So we can just clean, and it probably shouldn't do anything right now, but if you like copy over a new version, for instance, or you make changes to the source code, you want to clean every time. And then in order to compile, we'll call make. And this should hopefully work. This is a good way of verifying that your MESA installation is correct. And then if we just call run, it should go, and MESA starts running with some default parameters that you don't know about. And now output fills your terminal, and you get the steps of the stellar evolution. And every so often on the output, you'll see like a header table that tells you the different things that are being output. You have like the model number and the star age and so on. And then all these get output into this logs directory. I didn't run long enough to see them yet, but we'll do that soon. And what gets output it depends on what's in these history and profile column.list files that we'll go through shortly. So when you call run, what it's doing is it's pointing to the enlist, and that's telling MESA what it should be run with. So if we look at enlist, you can see all it does in this initial enlist is a redirection. We have these different name blocks: star job, EOS, cap, controls, and PG star, and all they do is say the information about these controls are in another file. Very useful to have redirections. And these name blocks are these things that I showed you on the website already. So if you look at the MESA website and you go to reference, you can look, for example, and here you find star job. These are all the different things you can include in this kind of block. And so you can include these, and yeah, one of the things is read an extra enlist, and that's what we're doing. So what you've learned here is everything interesting is in enlist project. So we can look at enlist project. And there, by default, what we have is an enlist to evolve a 15 solar mass star. So it starts with creating a pre-made sequence model. It says, don't save the model when we're done. Show on-screen plots. Some things about the opacities. Here you see the initial mass is specified in controls and the initial metallicity. And then we have some stopping controls. So this says basically stop at SAMs. This is when the nuclear luminosity over the total luminosity is 99%. So that's a decent indication of the zero-age main sequence. And then we have this control of stop near the zero-age main sequence set to true. And then here's a second stopping condition that won't get reached in this run, which is to stop when the central hydrogen fraction is depleted to a certain amount. And then there's some comments for additional controls that are just empty. You could put stuff there if you like. So we are not going to do a 15 solar mass star in this tutorial. I've prepared a separate INLIST for you that you can copy over. So that's, if we go back to the tutorial, yeah. So we've made and run and verified that it worked. So we're going to compute some solar mass models now. So we're going to change the mass, the initial composition, and the mixing length parameter so that we roughly get a solar-like model. And I've included an INLIST in the source directory. So let's copy that over. So if we look at source, there's INLIST project. And we'll just copy that over. And now, when we look at INLIST project, we see a different INLIST. Here, instead of computing a pre-main sequence model, because that would be somewhat time-consuming, we're just going to relax a pre-computed ZAMS model to something roughly like the solar composition. Initial helium abundance of 0.269, initial metallicity of 0.0187. Now, yeah, if you do want a solar model, you would have to calibrate it, and that depends on all the other physics that you input, like the assumed solar composition and the physics of the solar evolution, etc. There's an extensive number of controls and physics that you can include into your MESA run. We're just going to run something incredibly simple. The amount of detail you need in your INLIST depends on the project you're working on and the thing you're looking into. So we'll just do something very simple for the sake of the tutorial.
So wait, you
Yes.
said it takes one solar mass starting model,
Yes.
finds it on file, and just adjusts it a little to the new composition.
Yeah, exactly. Yeah.
Where does it find that initial model?
Yeah, there's this ZAMS directory. We can see this in star jobs, so ZAMS models.
Okay.
Yeah. So in data, star data, ZAMS models, those are where the pre-existing models are, and they the default value Z is 0.02, and so our relaxation is not very far away from that value. But of course, if you want like a really detailed ZAMS model, you should start from the pre-main sequence and include a nuclear network that has all of the species that you want to consider, et cetera. Yeah, absolutely. Yeah, so here we've only specified, 5 or so parameters, but there's thousands of parameters in MESA. So whatever you don't specify here, we'll take the default value that's in these references. And obviously the defaults are absolutely correct, and you should trust them with your life. No, it's clearly not the case. You should not trust anything, and you should test everything. You should test to make sure that your run isn't sensitive to the values you've assumed as the defaults. Okay, yeah. Here in the opacity controls, we want to make sure to set our Z base to be the same as the composition that we've set. It's sort of a technical detail. It's just for matching up the right opacity table. And then down here in controls, we have some fairly simple controls. We've changed the initial mass to 1, like the sun. And then I've increased the mixing length from 2 to 2.22, which gets us, in this case, a little bit closer to the sun. And then I've set a stopping condition to be a log effective temperature of 3.751, just to get us somewhere on the subgiant branch, just for fun of the run. We're going to include the physics of diffusion because it's nice to look at, and it'll show up in our plots, and we'll be able to see it clearly. And then finally, you know, the important part is we want to get stellar models for asteroseismology. So we want to add this line, write pulse data with profile equals true, and add atmosphere to pulse data equals true. And then I set the profile interval to 20. So that means when we run this enlist, we're going to be solving the stellar structure and evolution equations, and every 20 steps, we're going to output a detailed stellar model, telling us the structure of the model and giving us what we need to compute the oscillations of that model.
What does the second line mean, atmosphere to pulse data?
Yeah, good question. So, well, it kind of does what it says on the tin. Basically, when you output a MESA profile file, it's just the internal structure, you know, from the center point to the photosphere. Now, for oscillations, we want to also have the atmospheric data. And so this will append on, by default, an Eddington T-tau gray atmosphere. And you can see that in the pulse file that gets output. So by default, when you turn on write pulse data with profile, it's going to generate an FGONG file. And so in that FGONG file, you have the atmosphere. Yes, Jørgen?
The atmosphere must also be included in the surface boundary condition for the interior. So you say Eddington gray profile for the atmosphere. Does that mean that the surface boundary is also computed with the Eddington gray profile?
Yeah, that's a good question. Yeah.
Inconsistency in the model.
I think it should be. It's probably done consistently. I think Rich slipped out conveniently.
So it's your atmosphere is whatever you set it to in the default. So if it's not specified here, it should be Eddington T-tau by default, and add atmosphere to pulse data is always T-tau, I believe.
Okay.
So when you're doing asteroseismology, you have to set that to T-tau, or there will be an inconsistency.
But that gives you the atmosphere that was used for the modeling, interior modeling.
So
Yeah, that's a question.
What she says is you can change from Eddington T-tau to other parameters.
Oh, so sure, yes, that's right. But again, I mean,
But the asteroseismo code will use T-tau.
yes, yeah. But for the interior modeling, you need to set the surface pressure
Yeah.
as a boundary condition. That surface pressure comes from the atmospheric
Yeah.
model that you're using.
I believe that's done
And
self-consistently.
That should then be consistent with the atmosphere that's output to the oscillation
Yeah.
file.
It's my understanding that that's done properly. It could,
It's my hope. So.
yeah, it could be double checked, but
Yeah.
I mean, I don't know why it would be done otherwise. So, I mean, we can certainly check it, but.
You're young.
Yeah,
I have a question about the z-base parameter.
yeah.
I saw that in the defaults it's just a -1, so it's set to.
And then MESA will crash.
It will crash.
It'll say you need to set Z-base, as far as I recall.
So I've definitely run it without setting z-base before.
It will do nothing. It will set Z-base to whatever you have set for Z.
Ah, okay.
So it automatically.
Then I'm recalling maybe an older revision.
I was worried about running inconsistent metallurgy, opacity.
Yeah, sure.
Without realizing it, but
Yeah.
it does what I thought it does. It's okay.
Yeah, exactly. So now we're ready to run this this enlist. So if we hit run, again, our screen will fill with some output. So the first step will be this relaxation you saw that just went through, and now we're computing the evolution from ZAMs, and we can pull this up. So now you see some output being generated inside of our logs file. I think this is this not? Looks a little weird because, am I in the wrong directory? Ah, yes, I am in the wrong directory. Okay. Okay, now, okay. Yeah, that was my completed example. So now you see the kind of output that gets generated in the logs file. Oh, I forgot to mention an important thing. So before we run this, which I still have to do, so I'll cancel this run, we want to edit these profile columns.list and history columns.list to get the output we want. So just before we do that, I'll show you what it kind of looks like. So when we run MESA, we populate this logs directory with different types of files. So history.data will contain the evolutionary history that MESA calculates. So here you can see these are the different models that MESA has calculated. Here's the number of zones in each of the models. Here's the age of the star, et cetera, et cetera. So all the columns that get included in this history file are in history columns.list. And if you want to include some additional information, you can uncomment any of the lines, and you will get you'll get that information in your output. And so what I've said is that we want to go into history columns.list, and get delta nu and nu max because we're doing asteroseismology. So we can go in here, we can search for delta nu, and we just want to uncomment these in our history columns.list. And then these will be computed and added to our history output. So we can save that, and then we'll edit the profile columns.list. And there, I've said we want to get the Brunt-Väisälä frequency and Lamb frequency. So we can search for that. We uncomment Brunt N2 and also Lamb S. And now when we run, these things should be in our resulting outputs. So you see that this directory also gets populated with a profiles index and these profiles files. So we'll open this as well. Can I also, yeah. Yes. So the profiles index will relate the profile files to the history files. And these profile files are the detailed internal structure of your model. So this is profile1.data, looking at model number 20. It tells us how many zones, like there's 5 lines of header information telling us global properties of the model, like its initial mass, initial metallicity, the age of the model, the time step, etc. And then afterwards, you get the detailed internal structure. So you have the mass distribution, the spatial distribution, the internal temperature, density, pressure, etc. Yeah, and then composition, X and Y. So the detailed internals of this particular model at this point in time. And now this profiles index starts to get populated. So like, let's see, you have model number, and the more important thing is the profile number. So for example, history model number 80 will correspond to profile4.data. So if we look at history data, now we have this 80 down here. This is going to correspond to profile4.data. Okay, very good. Now we're ready to start doing some stuff while it runs. So we're going to make use of Python to analyze the output of MESA. I'll just get comfortable. Before we switch over to the Python component, are there any questions from the audience? Does everyone have this running? Or for those of you who are running it, is it going okay? Looking good. Yeah, Rasmus.
I just had a question. So how does it calculate delta nu and nu max that it outputs?
Scaling relations.
Okay.
Yeah. That's a very good and important question. We're going to be calculating a more accurate delta nu using the frequencies. Yes, exactly.
It might be better if I really want to run it and get frequencies, even just delta nu and Umax to run it with GYRE actually.
Yeah, well, so GYRE won't give Numax. That's a quantity that we don't know how to calculate from first principles. So that will always come from the scaling relations until we improve as theoretical astrophysicists. But delta nu, certainly, we want to calculate using GYRE. You'll find something like a 2% difference between the asymptotic value and the computed value. And then that computed value also is going to be discrepant from reality because it doesn't take into account surface effects. Yes, Jørn?
You said the scaling relations for delta nu. So it's not using the integral expression for the asymptotic?
Okay, yeah. For delta nu, I think it uses the asymptotic. Yeah,
That makes more sense.
yeah. So the inverse integrated sound travel time. Yeah.
Can you give us, so are there particular things when you're doing the seismic run that you need to be extremely careful that you set, like the atmosphere boundary?
Yeah. Good question.
Like a book of things that we really should pay attention to?
Well, yeah. I mean, the most obvious thing is that you need to be able to output the pulse data and add the atmosphere to the pulse data. The atmosphere is quite important. Without it, you'll get incorrect oscillation properties. Yeah, and other than that, I think it comes down to your science case, what you want to include in the models. But I think for a large part, MESA takes care of a lot of this for you. Yeah. So it can be very important to increase the resolution. This can often be done within GYRE itself, because GYRE can take a MESA model and remesh it to have sufficient resolution that you need. But that's assuming that your MESA model has enough information for GYRE to be able to do that interpolation and remeshing accurately. So one control that you may want to play around with, well, in general, is mesh delta. That's should be in controls. Sorry.
Just demesh is
So mesh delta coefficient will change your spatial resolution, and it tries to do it in a way where it intelligently adds points. So it doesn't just, put points everywhere, but there's a great number of controls after mesh delta coef that tells you where the points should go. So in your specific case, if you want additional resolution in a certain point, you can also adjust those specific controls. Yeah. Did you want to add something?
No. Well, Rich is back if you wanted to address the atmosphere boundary.
Oh, yeah. Jørn had a question, but I don't know if it's better to duke it out later. Or I think Jørn's question was just whether the atmosphere in the MESA run is computed self-consistently with the atmosphere that's output in the pulsation data in all cases.
It is now.
It is now.
It wasn't, 150,000 revisions in the past. That was before, that was back when the internet was black and white. So since probably 2018,
Okay.
an inconsistency between atmosphere reconstruction and interior model has been fixed.
Okay, there you go. Okay, so your question had some context. Okay, very good. And now our run has finished, so that's very nice. So our logs directory got populated with some files. I don't know if I mentioned this already, but every data file that we've output now comes with a corresponding fgong file. So if we look at one of those, you can see an fgong file. And the structure can be somewhat opaque, but I've included a link to what an fgong file consists of. So at the beginning, you have some global parameters like the mass and the radius, etc. And then you have the internal structure, distance to the center, the mass distribution, etc., in a slightly opaque to read format. But fortunately, GYRE knows how to read it. And also at the end, I'll show you how to get Python to read it very conveniently as well. But that won't be part of the main tutorial. So for many of you, hopefully this initial MESA run has finished. And we're now ready to start doing some plots to start seeing what we've calculated. Have people finished the run, some of you? Yeah? Very good. Okay, excellent. So first things first, we'll import some packages. The OS package in Python for determining the paths to our files. We'll import NumPy for doing some numerical calculations. SciPy we'll use later on for interpolation. Pandas is a very convenient package in Python for reading in regular data files. And since MESA outputs its data in a convenient tabular format, we can use that. Matplotlib we'll use for plotting. And then we're going to use IPy widgets to create sliders to advance through our evolution so we can see the plots change as we evolve. And then Seaborn just for some pretty plots. So we should be able to run this, and it should run okay. I've also included a matplotlib RC file just also for some pretty plots. So the first thing we'll do is we'll read in our MESA data. So I'm going to point to the logs directory. So that's in work/logs. And I'm going to write a function that will allow us to read this, load the history file into Python. And I've made it as a function so that we can do, later on, we can compute a grid of models and read them all in. So all this is doing is it's looking at pandas and using its read table function and pointing to the history file. We have to skip the first 5 rows because there's the header information there, and we just want the run information. And then we set our delimiter. This is a regular expression that says to split on variable amounts of white space, right? And when we do that, we get out this, this convenient history file, which we've just looked at. And now you can see how things in our run changed over time. So like the evolution of delta nu and nu max over the age of the star. And you can see our run went until 10 gigayears. So solar-like model going all the way to almost the base of the red giant branch. And you'll see that visually soon. Okay, next thing is we'll parse the index, which relates the history file to the profile files. So again, I've made a function. We're going to read this table, the profiles index. We have to specify what the names are. They contain the model number, the priority, and the profile number. And we skip the first row because there's that header information. And again, we split on variable white space. And then we get this nice table telling us, you know, profile 6 is history file line 120 or model number 120. All good? Does it make good sense? Fantastic. And then finally, we have get history, which this is just a convenience function that will allow us to relate our profile file to the history file using the index. So we'll take a profile number and, I should say, I called the history file df. This is sort of out of habit. It's just for data frame because in pandas, you know, when you read in a table, it's called a data frame. So it's a somewhat, yeah, just convenient name. So all we're doing is we're looking in the index and we're finding the place where the index.profile number equals the profile number that we've supplied to our function. We're grabbing that model number and we're returning the row in the history file that corresponds to that model number. So here's an example for profile number 5. We get this, this row in the history file. Okay, so with that in mind, these convenience functions defined, we're now ready to make a basic plot. So again, I'll make a function because I want to be able to apply this to different profile numbers, right? Because later we'll make a slider and step through. So for the HR diagram, it's not super important because this is the total evolution, but we'll indicate where we are in the evolution with the profile number. So first things first, we'll use matplotlib to plot the HR diagram. So the effective temperature and the luminosity. And because these are log quantities, I'm just doing 10 to the power of them first to get to get them in normal units. Because we did a relaxation, the first point in the history file is often just a relaxation step. So I just cut that off by saying, let's start at the second point. So that's why we do this, this slice here. And then the rest of these, for those of you who aren't familiar with Python, this just says set the line width to 3, the color to black, and we'll give it the label evolutionary track. And then here I've added some code to say where we are in the profile files. So this is just going to highlight which profile we're on and add a label saying what age it is. We have to invert the x-axis, of course, because we're astronomers and temperature goes this way. We add some labels using this syntax so that we get some LaTeX. We'll add a legend and a title, and when we call it, hopefully you get this nice HR diagram. So here in black, you have the contents of the history file plotted, and then these blue points are now where the profile files got output. And if you remember, we set the profile interval to 20, so there's 20 models in between each of these points. You can see, by the way, that there's some jaggedness to this run, and that's because I haven't adjusted any of the numerical parameters for this run. So if you want like a smoother evolution through the HR diagram, you can adjust things like the mesh delta coefficient or the time delta coefficient to get different temporal resolution. There's also controls for setting how far the evolution can move through the HR diagram. I think it's called HR delta. So, you know, if you want to prevent the jaggedness. You can also do things like setting how much of the central hydrogen abundance can change from model to model. That also gives you good smoothness along the main sequence. So hopefully this worked for everyone, and this nice plot comes up and you can see our run. Okay, so now we've plotted the history file. Let's look inside of some of our models. So now we need another convenience function called load profile, which will allow us to read into memory one of these profile files. Yeah, and all we have is the profile number, and we point to the logs directory, which is a global variable that we have. And we'll say we're just going to call pandas again with read table, and we're going to point it to logs directory, so logs/profile, and then the profile number dot data. We skip the first 5 rows because it's a header, and we split on variable white space. And then you can see, for example, here I'm loading profile number 5. And here you see the internal structure of the model: mass distribution, spatial distribution, composition, etc. So that should work. And now we want to get all of the profiles. So we will use this next convenience function, get profiles. We'll pass in the index in the logs directory, and we'll call this load profile function on all the profiles in the index, right? So now we'll loop through the index and load up all the profiles, and that should work out. Okay, so let's look inside of one of our models. So here we want to plot the internal chemical composition for one of our models. And for some nice guidelines of where we are, I'll pull out the zero-age main sequence metallicity. So we have the ZAMs X and Y, and that's just by grabbing the first profile that we've calculated and grabbing their hydrogen mass fraction and helium mass fraction. I've also put on the primordial helium abundance, which is a useful reference point. And now I've made this function that will plot the composition of a given profile number, right? And here we're plotting profile number 5. So here we grab the profile that we want, and because the indexing is different, we're going to subtract 1. You know, there's a off by 1. And profile 1 goes with into index 0, right? So just take care of that. We'll get the spatial coordinate x, so 10 to the log r, and we'll normalize it by the maximum value. So this will give us a relative radius. And then we'll plot x versus the hydrogen mass fraction, which we'll label and put in black, and then the helium mass fraction. You can see that down here. And then I've added lines for the protosolar composition. So you can see in these dashed black lines, you get the initial hydrogen and helium abundance. And you can see at this profile number 5, the helium abundance has decreased and the hydrogen abundance has increased. Why is that? Oh, you didn't expect a quiz. All right, Jörn, you can. Exactly, from diffusion, yes. Well done. Yeah. And in fact, somewhat fun, the helium abundance in the envelope of this model, due to diffusion, is now lower than the primordial value. But of course, the initial value is higher, and the internal values are higher. Okay, so now we can look inside of our model and see the internal chemical composition. And next, we'll make a propagation diagram. So here, a propagation diagram tells us where the P modes and the G modes can propagate inside of our model. So we'll grab the history, we'll grab the profile that we want, and we've already asked MESA to calculate the Brunt-Väisälä and Lamb frequencies. So those are conveniently available to us inside the profile file. So we can just plot those. And then, yeah, this is just some code for filling the regions. So yeah, the G modes are below both the Brunt and Lamb frequencies, and the P modes are above both. And then we'll add a line for nu max, and we'll color the region around nu max where we roughly expect oscillation modes to be visible. So that's like roughly 5 or so radial orders around nu max, which is given by delta nu. And there you can see our nice propagation diagram for this model. Yeah, down here you have the buoyancy cavity, and up here you have the Lamb cavity. Here you have nu max, and this is roughly the observable region. So at this point in the evolution, you expect only to observe pure P modes whose L equals 1 frequencies turn around at this point in the interior around 0.3 or so. Okay, yeah, sorry, yeah.
Looks like the model only extends to 1 there.
Yeah, that's because I've normalized.
Yeah, but still, with the atmosphere added, it's just
Yeah, so here we've only plotted the profile file, and the profile file does not contain the atmosphere. Only the FGONG files contain the atmosphere. Also, somehow it didn't output. I'm just going to change my directory for complete. If you run into this error, it's because you, like me, I know why. So here, when I edited my profile columns, I accidentally commented out Brunt N2 when I meant to get Brunt N. Yeah.
Very pedagogical, sure.
Exactly, yeah. So that's why I got an error. But now when we fix that and rerun MESA, now now the plot should work just fine. Okay. Now, that was all MESA, right? We can get a nice propagation diagram just with just with MESA. Now we want to get to GYRE. So now we want to compute some frequencies with GYRE. And I've supplied an example inlist with GYRE. But first, let's go to the GYRE website. So GYRE is a wonderful oscillation code, as I mentioned, made by Rich, and it has very nice extensive tutorial on what GYRE is doing. So GYRE is computing the eigenfrequencies of your model. Take the stellar oscillation equation, the stellar structure equations, you introduce a perturbation, you linearize, and then you solve them for the eigenfrequencies. And GYRE does this scan efficiently, can do it in parallel, and can be applied to a lot of different types of stars. So that's what we'll do now. So I've prepared a simple GYRE inlist for you. So let's copy this over. can copy. So we go to our logs directory, and we'll copy the gyre list, which, yeah, I went to the logs directory first. If you do it as written on screen, it'll work out. Okay. Live demos. Okay, now we have a gyre.in file. So if we look at gyre.in, of course, you can see all this information on the gyre website if you look at nameless input files. So the first thing we need to do is specify which model we'll be calculating frequencies for. So in this case, we'll point at profile1.data.fgong, and we have to tell it that it's going to be an fgong file. And then we'll say that we want to calculate modes of spherical degrees 0, 1, 2, and 3. So the radial and non-radial oscillations that we expect to see in sun-like stars, and in fact do see. And then for the oscillation parameters, yeah, I mean, you can sort of do what you want here. So here I've specified the JCD outer boundary conditions, but there's many others, and the JCD variable set. This sort of depends on what you want to do. I've said we want to normalize the inertia by both the horizontal and radial component. Again, this is somewhat technical, not super important for the purposes here. And yeah, the reference X values at the photosphere, again, that's for the inertia normalization. We have to specify the scheme that we want to use for calculating the frequencies. So here we're using the fourth order scheme. For your own purposes, For your own purposes, I recommend that you try out the different numerical parameters and see that the frequencies converge to the level that you need for your scientific application. So for example, if you're working with, let's say, Kepler data or test data, you can see the uncertainty on your oscillation frequencies, and then you can recalculate your theoretical frequencies with different numerical properties, and then see that they change by much less than the uncertainties in your observations. And then you say, okay, this is probably sufficiently converged for my purposes. Okay, was there a question? Yeah, sure.
Just regarding at the very beginning to the file formats, there are various file formats. I always use the MESA one.
Yeah, sure. So by default, MESA will output an fgong file. We might consider changing this at some point. Yeah, I believe, did you create fgong file format? Are you the inventor? Yeah, so unfortunately we might move away from Jørgen's format. But of course the capability to output fgong will always be maintained, but the default might change at some point. Anyway, by default we output an fgong file format. But for many purposes you want to output a gyre file format because it contains additional information that's not in the fgong file that's useful for some purposes. Like for example, I think if you want to consider maybe non-adiabatic effects or rapid rotation and so on, Rich has included additional variables and gyre knows how to handle those additional variables. So in your MESA list, you may want to change that. Okay, what else do we have here? We have some remeshing. Oh, sorry. We have some scanning controls. So we'll construct a linear grid and we'll search between 1,000 microhertz and the acoustic cutoff frequency. And we'll do 100 such searches.
Linear grid meaning it's equidistant?
It's equally spaced in frequency from 1,000 microhertz to whatever the value of the acoustic cutoff is. And then here's some remeshing controls. You can read about these on the website, but this tells us how we're going to redistribute the points inside our stellar model. Sorry, did you still have a question?
He just asked where can we find the default control files for gyre and
Yeah.
the gyre read the docs.
Yeah, exactly. gyrereadthedocs.io. It's also in the tutorial linked at the top. There's rotation controls. We won't use that. Here we'll specify the output of the adiabatic oscillation program. So we have a summary file, which will be, I call it profile1-freaks.dat. It's a text file, and inside that text file we'll have the spherical degree, the combined P and G radial order, the P mode radial order, the G mode radial order, the frequency of the mode, and the mode inertia. And the units will output our microhertz. Okay, with that all in mind, in theory, this will work. Oh yeah, I have to set my gyre directory.
No, no, you have to remove this
The
$sign.
dollar sign?
No. It's because I haven't set my gyre dir.
It's a variable.
Yes, all I. I might also have to make. Yeah. What? Yeah. So if you've set things up better than I have in advance, then when you run this, you'll get the gyre output and it will produce a nice log file. So if I go back to my completed tutorial, you'll get out this file. So in this file, it has all the things that we told it to output. The radial order, the frequency. So the frequency comes in two components, a real and imaginary component. If you include non-adiabatic effects, you can look at the imaginary component of the frequency, and that will tell you about the growth rate. But here we're only doing the adiabatic calculations, and so it's 0 here. And so we'll only look at the real component of the frequencies. And so now we're ready to parse this file, which hopefully worked out for everybody. So we can, again, create a convenience function called getFrequencies. So we'll pass in the profile number and the logs directory, and we'll read out, I called it profile and then profile number dash frequencies. You can, of course, call it something else if you want, but then this function won't work for you. And then we'll again use pandas to read it in, skipping the first five rows and delimiting on white space. And so now we have the frequencies of our stellar model all ready. Spherical degree, radial order, frequency, mode inertia, all ready to go. So those are the frequencies of one model, but it's nice if we get the frequencies of all of our models. So I've prepared a little script that will calculate the frequencies of all of the models in our logs directory. So I'll just show you that very quickly. So we have gyre6freaks.sh. It's a shell script that will take in a gyre file or an fgung file and prepare an inlist and calculate the frequencies. And it'll be basically the exact same inlist that we've just prepared in this gyre.in file, and it'll just point to the whatever file you read in. There's also some flags to change these parameters, like if you only want radial modes or only dipole modes, etc. We can take a quick peek into here, but it's not really the point. Yeah, in the beginning, all it does is parse the command line tokens, like the input file, etc. And then this was the helpful help message. And then it starts preparing the enlist. So like if you wanted radial modes, yeah, or dipole modes, it'll change the enlist appropriately. And eventually, at the end, it prints out this big enlist and then just calls gyre on it and then saves the file name as in that same format that I just gave. So like profile 5-freaks.dat, for instance. So
And that script is not a standard part of
no, it's not the standard one. I've just prepared it for the tutorial. Exactly. Which means if we now do this loop for fgong in star.fgong, you can you can get frequencies for all our models. And indeed, when we run this in a loop, we should get out all these different frequency files, right? So now we have frequencies for every one of our stellar models. And so here's another helper function where we call get frequencies on each of our profile files in the logs directory, and it should work. And now we're ready to plot in a shell diagram. So in a shell diagram is a convenient way of looking at the theoretical oscillations of our stellar model, where we, on the x-axis, we plot the frequency modulo the large frequency separation. On the y-axis, we plot the frequencies of the modes, and we get these nice, basically straight lines with all the modes lining up, and that's because the modes are roughly evenly spaced in the large frequency separation. So how do we do this? Well, we take a profile number, we get the history information for that profile number, and we'll grab the profile file and the frequency file for that given profile number. Remember, the indexing is different, so we're off by 1, so we have to remember to subtract 1. We'll grab numax and delta nu from the history file, which MESA has computed for us. Oh, this is not right. Okay. Here we only want modes that are below the acoustic cutoff frequency, so we'll grab the modes with the frequencies that are less than 5/3 of numax. To calculate our own delta nu, we're now going to grab just the radial modes, and we'll grab the ones, so for the radial modes, these are the modes with spherical degree L of 0, and because we want to be in the asymptotic limit, where n is much greater than L, 10 is a lot bigger than 0, so we'll call that asymptotic. Far bigger. You can hardly think of a bigger number. And then to get delta nu, we'll take the average difference in successive radial modes. Of course, there's different ways to calculate delta nu. This is a simple way of doing it, and one that at least visually appears to be pretty effective.
Quick question.
Yeah, sure.
So the two lines about calculating fraction, you have a 5/3 there. Doesn't that give 1? 5 divided by 3 integers?
No. That would be 5//3. So that's how you do integer division in Python, yeah.
Python 3. So if you did Python 2, then you would.
You are correct.
I would put 0.0 there, just like out of paranoia.
Yeah.
Yeah.
You can do as you wish.
Gives you a little there, rather.
Yeah, exactly. Yeah. Okay, and here we're just looping over the different spherical degrees, grabbing the spherical degree from the frequency file, right? Putting this into a new data frame called news, for frequencies. We'll plot the frequency modulo delta nu against the frequency itself, color it with these colors I specified above, and label it. Add a legend. We'll add a line for delta nu. We'll add a line for numax. And we'll set the limits to be a little bit above the acoustic cutoff frequency, and just a wide enough window so we can see all the models. And that gives us this a shell diagram for this model 5. Okay, so now we've calculated the evolution, we've calculated the frequencies, and we've prepared all of these helper functions that should in theory work on any of the profile files that we've looked at. And so now we're ready to look at the evolution in real time using all these functions that we've built up for the different plots. So we'll just make a new function called plot panels. We'll have 4 subplots, and in each one of those subplots, we'll just plot the 4 things that we've made by passing in the given profile number that we have, and we'll plot them all together, and then we'll use the IPython widgets to make an interactive plot that allows us to scroll through our plots and look at things in real time. So now we have the 4 panels we've made, and we're looking at profile number 1. So here we are on the HR diagram. I've highlighted the first point. We're basically at the 0-age main sequence. You can see the age is about 0 gigayears. You can see the internal composition. it's flat because we're at the zero-age main sequence. So yeah, we have a uniform initial composition. You can see the shell diagram. We have a great number of modes where the nu max is about, let's say, like around 4,000 something microhertz, and delta nu is like 160 or so. And then you have the propagation diagram here where you can conveniently see we have a convective envelope and also a small convective core at the zero-age main sequence. And again, we see pure P modes. And so now we can start marching our evolution forward, and we can see how things change over time. So now we've had a little bit of hydrogen fusion, increasing the helium abundance in the center. And because of diffusion, we've slightly decreased the helium abundance in the envelope. And you can see our convective core has gone away. And as we go forward, you can see how nu max and delta nu both go down, and our internal chemical composition changes. So now we have more helium in the interior than hydrogen. And we go forward a bit more. We get some nice evolution. You can see now we're turning off of the main sequence. We're at 8.5 gigayears. And you can see the buoyancy frequency starts to increase in the interior, and we start to get to the very interesting phase of evolution where you start to see mixed modes and avoided crossings appear. And so, yeah, now you can see these nice bumped modes because this buoyancy frequency is now containing G modes that are propagating in the observable region. These modes are coupling with the P modes in the outer envelope to create these mixed oscillation modes that get bumped throughout the shell diagram. Very good.
Bravo.
Thanks. Okay. So that's a nice basic tutorial that gives you the theoretical astroseismic evolution of a sun-like star nearly to the base of the red giant branch, showing you P modes and mixed oscillation modes. I prepared a little bit of additional material. There's only 15 minutes left, but we can go through it somewhat quickly. So not only are the frequencies of the modes interesting, but the eigenfunctions of the modes are interesting as well. And so we can modify our GYRE inlist to have it output the eigenfunctions. So all we have to do is go to our gyre.in file and modify this adiabatic output block. And in this block, we already have this stuff here. We're going to add detail files. These detail files tell us, they're similar to the profile files, but they're for the eigenfunctions. Here we have a template that tells us where we should output the information. I make a new directory to contain the eigenfunctions because there's a large number of them, and your logs directory will just be completely full of eigenfunctions. And if you run it on two models, it'll overwrite each other. So I create a new directory for each one called profile1-freaks. And I specify the spherical degree and the radial order will be in the file name. And then in this, in the eigenfunction file output, we'll have the spatial coordinates, and then we're going to also add, here are the radial and horizontal displacement eigenfunctions. So we create a new directory, and we call gyre on this file again. Or alternatively, you can just use this script that I prepared, and you pass it this -e flag, and it'll automatically add this stuff and calculate the eigenfunctions for you. So once we've done that, we can then again write a nice little helper function that will allow us to parse eigenfunctions. You run that, you should get out the radial and horizontal displacements, and then we can plot them. So again, we load up a, we make a function that will plot for a given spherical degree and radial order what the radial and horizontal displacement looks like on the inside. And again, we can use sliders. So now we can look through all the eigenfunctions of our model. So this is L equals 1, n equals 15. Here you can see yeah, this is what the oscillation mode is doing. This is a mode of a certain frequency, and this is how the interior is basically moving around due to this oscillation mode. You can see the horizontal displacement is very small compared to the radial displacement. The situation would be the opposite if these were G modes. And yeah, we can conveniently change the spherical degree. So you can see how modes of lower spherical degree have displacement deeper inside of the star. And as you increase the spherical degree, the displacement moves outwards. And similarly with the radial order, we can change it around. The radial order tells you how many 0 points are inside of the star. And you can see that directly in the radial displacement eigenfunction. The number of oscillations increase as you increase n. Yes, very good. Okay, and the last thing I want to tell you is you can, of course, I don't have time to go through this in great detail right now, but you can, of course, make a grid of models very conveniently and then plot the properties of the grid. So here I've made a directory called grid, and I've moved over our work directory to grid, and I've modified the inlist to stop at a central hydrogen fraction of 0.1, just in the interest of calculation time. I was a little ambitious with how much we might be able to get through. And then we're going to add log directory and call it 1 in controls, and that's for 1 solar mass. And then we're going to make a loop that'll go through and iteratively change the parameters and then output the parameters to a different log directory. And we're going to go through different masses. And for each mass, we'll change the log directory to point to that mass. So here's a bash function that will change our inlist. Probably many of you in this room have written your own version of this, where basically, you give the name of the parameter you want to change and the value you want to change it to, and the file name of the inlist where this change should occur. So for example, change initial mass to 1.3, and then in my case, by default, it'll apply it to inlist project. So because we've set this up, we can now make a simple loop in bash. So we'll loop over these masses for m in 0.7, 0.8, 0.9, etc. up to 1.2. We'll change the initial mass to that value. We'll change the logs directory to point to whatever we set, and we'll simply call run. And so it'll calculate all these masses, and then for each of these masses, we'll loop through the fgong files in our logs directory and calculate the frequencies of those resulting models. So with hopefully fairly simple code, we get a nice grid of models. And then we can visualize them, for example, in the, well, I guess JCD doesn't like it to be called the CD diagram. I didn't know until yesterday that he'd be here. Oh, it's okay. Okay, it's fine. He's okay to be honored with. Yeah, so.
The county diagram.
Okay, sure. So this is an amazing diagram that Jørn first made, what, in 1984 or so? Yeah, and so here you see the basic physics of astroseismic evolution. Up here you have the masses, the different masses in our grid that we just ran, and here you have the central hydrogen abundances. And so you can see how the large and small frequency separation change. So the large frequency separation, you recall, is the difference in frequency of successive radial modes, right? Which is a proxy for the mean density. And the small frequency separation is the difference between the L equals 2 and L equals 0 modes. And this turns out to be, as you can see, a proxy for the core hydrogen abundance, and hence a proxy for the age. And so if you observe the large and small frequency separation of a star, you can basically use this table, use this as a lookup table to directly determine the evolutionary state on the main sequence. You know, how much hydrogen is left in the core of that star. Yeah, I won't go through the code to make it, but you can see it's fairly simple. So just to be very explicit, here, for example, is a 1 solar mass track, and this is directly what you get out from the run. You get out its large and small frequency separation as it evolves from the 0 age main sequence to the terminal age main sequence. And then these lines are just connecting the different tracks at values of constant core hydrogen abundance. Okay, very good. Very last thing I'd like to tell you about are a few additional resources that I think are useful to people who like to do this kind of stuff. So the first one is TOMSO, made by Warwick Ball, and it's tools for models of stars and their oscillations. And you can see on the left, there's utilities for different things that are convenient, like FGONG, GYRE, MESA, etc. This is basically like if you don't want to write your own routine for reading in FGONG files, this is done for you. So you can conveniently load things into Python. I think it also has a few plotting routines, etc. So I found this very convenient. I use it quite a lot. Because, for example, as Ragnar pointed out, the FGONG files have the information about the atmosphere, which the profile files don't have. The FGONG files are also more smooth. You'll find kind of discontinuities in the profile files might not be sufficient for detailed astroseismic analysis just to rely on the profile files. You might want to use the FGONG files or the GYRE files. The Astro module can be very useful. If you want to model a particular star, the Astro module contains optimization routines where you put in the frequencies and spectroscopic information of that star, and it will iteratively run MESA and try to match those observations. Of course, it can be very convenient to write your own external programs to do this kind of thing, but this is also quite handy. So Astro will find you a decent stellar model for your observed star. Also, Tulips is quite cool. It's new from, is it Ava Laplace? Yeah, is she here? No? Okay. Okay. So this is a very nice plotting routine that will read in MESA data and show you things like, you know, what does your star look like at a given point in time. Also, there's these nice diagrams where you can look inside of the star and see things like, what's a good example? It's really cool for massive stars. You can see like the internal chemical composition. It's quite neat. You can spend a lot of time looking at these diagrams. And then the last thing I'd like to point out is mesastar.org, which has a lot of useful materials. So you have INLISTs, for example. When people publish papers using MESA, we greatly encourage you to share your INLISTs. And so you can see how other people did their calculations. Yeah, it's an open source code. We want your contributions. We want you to share with others how you've done things. And these are great starting points for doing your own projects. There's also a great number of educational materials online. So for example, all the summer school materials are here, and you can see detailed examples of how to do different things. One of the best things, in my opinion, is Josiah Schwab's tutorial, which teaches you how to modify MESA source code through runstar extras to implement your own additional physics. You know, if you want to like add a cooling source, for instance, or add a custom stopping condition that's based on some Fortran code, or if you want to run GYRE inside of MESA, you'll do it through runstar extras. So that's basically the materials I wanted to share with you all today. As you all see, they're available online and will remain available online. So please feel encouraged to use this and make reference to it. If you weren't able to follow the tutorial today, you can follow it some other time. Everything I showed today is available online, and I really hope it's useful for everyone. And yeah, I'll take some questions if there's any remaining with the last 3 minutes. Yeah, sure.
Does GYRE do non-adiabatic calculation?
Yeah, absolutely. I can show that very quickly. So in GYRE, you have where should it be? Is it oscillation parameters? It's certainly in here. Is it oscillation parameters? Am I not seeing it? Oh yeah, no. Yeah, here, there's a non-adiabatic flag. Yeah, and this, of course, enables 2 more differential equations in the calculations. Yeah, and that'll give you things like growth rates. And Rich has a phenomenal tutorial on the MESA education page where he computes the beta Cepheid instability strip. You can see it here. You can go through Zenodo, but it's also on his GitHub. You can see how he looks at how the imaginary component changes from negative to positive to find out when you expect different kinds of beta Cephei oscillations. Yes?
May I be unreached up here? Just to point out that it's wonderful to have an adiabatic part of GYRE, but it doesn't include effects of convection. So using this for cool stars is a recipe for disaster.
Yeah, that's absolutely true. Yeah. Yeah, so in a full non-adiabatic treatment, you would want to consider the effect of convection on the pulsations. And therefore, because GYRE has so-called frozen convection, you would not be able to get the growth rates of the kinds of oscillations that we've done here, which is why we stick to the adiabatic oscillation calculations. That's a good point.
In other words, only the radiative damping approach is included.
Yes.
RSP takes care of that.
RSP can do radial oscillations of, I think, classical pulsators, but I don't think it can do, well, that's a good question. Maybe it can do the radial modes of the sun, but I'm not entirely sure. Yeah, it can.
Well, in principle.
In principle.
But it's pretty tuned to TASC6.
Okay, yeah. Okay, that would be something great to look into.
It only does radial oscillations.
Yeah, sure. Yeah. I don't think anyone knows how to do non-radial, non-adiabatic. Yeah, with time-dependent convection.
Yeah. Well, when we can figure it out, I'll try and figure it out.
Yeah, Rich is gonna push it. Yeah.
One question. Is there any perks or pros and cons installing GYRE Expert? Because I always installed it Expert and now I discovered it already there.
No, I think MESA comes bundled with the latest version of GYRE. It's only if you would want to use an older version. Yeah, I don't think there's any advantage to installing it separately. It's the same code.
The only advantage is if you want to use the development version.
Ah, yeah.
Straight from GitHub.
Okay, I think that's all the time we have. So thank you all for coming. I hope it was useful. Thanks to the TAs for helping. Greatly appreciated. And yeah, have fun with MESA and GYRE.